The orbiting Russian module is known as Zarya, which means sunrise. Next, the first American module, known as Unity, sets off inside the cargo bay of Space Shuttle Endeavour.
Liftoff of the Space Shuttle Endeavour.
Unity is now chasing Zarya through space at more than 17,000 miles per hour. Two modules from two superpowers are about to dock.
First thing we have to do is to open up the payload bay doors.
Can you imagine how important it is for these two modules to mate?
Unfortunately, before both modules were launched, engineers spotted a problem.
Not all the pieces got to be integrated on the ground before they were launched.
Neither Zarya nor Unity were originally designed for the ISS. Their docking systems wouldn't fit together.
The Russian hatches are all round, and our hatches are all square.
I mean, this is fundamental to the International Space Station, and what you have are two things that don't mate.
And so, what do? Well, you make an Adapto Lego block connector thing.
The L-shaped Lego thing they came up with is called the Pressurized Mating Adapter, or PMA. Not only does this accommodate the different shaped hatches, it also has a precision-engineered docking ring for grabbing hold of another module and perfectly aligning it. Vital if a reliable airlock is to be made. This is the moment of truth. Latches on the inside of the docking ring finally make the connection and pull the modules together.
Houston Endeavour, we have capture of Zarya.
The International Space Station is born.
It was amazing. I mean, here we are. We got airborne. We had Unity in the bay. And when we left a functioning space station ready for the next module to come up.
In the 20 years that follow, engineers from all around the world join the project, building their own space laboratories and bigger living quarters. But every one of the modules was constructed on Earth, and it takes a supreme international effort to launch them all successfully into space.
It took a long time to build Space Station. We have to fly everything up, we have to connect all the modules, put them together. So that took over 40 missions. Modules came from all over the world. We have the US modules from NASA, we have the Russian modules, we have the Japanese modules, and the European module, you name it.
And it costs around $10,000 to send every pound of weight up here from Earth.
And what's cool about this module, it is actually the very first piece of the space station that came up in 1998.
It's been occupied continuously ever since then. So if you think for 18 years, there has always been a human presence in space.
Today, the ISS is enormous. By far the largest space station ever created.
It's actually big enough if you have a good pair of binoculars, and when it's flying right overhead, you can actually see it. Normally you look at a satellite and it's just a little dot, but the ISS is big enough that you can actually see it as an extended object.
It's so vast, in fact, that it would dwarf Times Square. At an astonishing 357 by 240 feet, it has more living space than a 5-bedroom home. But the larger the International Space Station becomes, the larger a very obvious issue becomes, too. Air. In space, there is none.
It doesn't provide a life support system for us, air, oxygen. And so if we have a home in space, we need to provide all of that.
The average adult breathes close to 4,000 gallons of air per day. With a crew that can be up to 9, the ISS must supply a huge amount of it. And it's not coming from outside those windows. cruising outside the Earth's atmosphere, the International Space Station has to provide everything the astronauts need to live. And breathable air is first on the list.
Their very survival really depends on the things that we provide them. And you're also having to deal with the fact that at any point in time, if one of your system fails, you have a very limited amount of time to either get something from Earth or to get back to Earth as quickly as you can.
In a crisis, an emergency supply of oxygen can be sent up by rocket. 3, 2. With technological advances, spacecraft can now rendezvous with the ISS in 6 hours, if everything goes as planned. But even when a cargo delivery is successful, there's a price to pay. The cost of each mission is colossal, almost $200 million.
It's expensive to bring a kilogram of anything up to the space station. And to spend all that money just to bring up water and oxygen would be an incredible waste.
The ISS needs to make its own air.
The oxygen on the ISS can come from a delivery from Earth, and then they're stored in tanks. But the ISS is also capable of generating oxygen on board.
On Earth, we take air for granted. In space, each astronaut must be supplied with 1.85 pounds of oxygen per day, 365 days a year, to avoid suffocating. In the very heart of the ISS is an unassuming machine about the size of a trash can. It's this that holds the secret to keeping astronauts alive. Incredibly, it generates oxygen from nothing more than water.
So what happens is you have some water, you feed some electricity through that water, and the electricity will split that water into hydrogen and oxygen.
The oxygen comes off as bubbles at the positive electrode, the hydrogen at the negative. But again, being in space turns something that's straightforward on Earth into a major engineering challenge. The bubbles of gas won't come out of the water.
In your high school chemistry lab, the gas just bubbles up to the surface because the gas is lighter than the water, and therefore it goes up. Gas is not lighter than liquid in space because gas doesn't have any weight and liquid doesn't have any weight. So you produce gas bubbles and they just sit there. And what we generally do is we centrifuge it. So you spin it all around, and the liquid, being denser, it doesn't weigh anymore, but it still has mass. So it's denser, and it goes to the outside, and you can then separate the liquid from the gas.
The hydrogen gets thrown away, gets pumped into space, and the oxygen is used for the ISS air supply.
There's enough capacity on board to generate 5 to 20 pounds of oxygen a day. More than enough for the crew. In the extreme environment of space, making air is just the first challenge. The ISS has to keep it, but it's under constant threat of a breach in its hull.
There is so much space junk up there now.
There's the potential for it to puncture the outer wall of Space Station.
I was taking pictures out one of the windows, and it was a nice clear window. I came back sometime later to take another picture, and there was a great big ding in the window, about a 5/8 of an inch in diameter from a micrometeorite impact. And we had to take pictures, close-up pictures, send it down to the ground, and it had to be analyzed to see whether it was going to be a threat when we entered.
If you pop a hole in Space Station, the atmosphere is going to leave very, very quickly.
No atmosphere means no oxygen, and the consequences of that are obvious. So how does the ISS deal with the threat of colliding with meteorites? The International Space Station is the largest man-made object that's ever orbited the Earth. And it's racing around our planet at 5 miles a second. But on board, that's hard to appreciate.
How do we sense speed if you're in a car, for instance? You know, you have the road noise, you have the wind going by, you have billboards or trees going by your window. None of that exists in space. The only way you get a visceral sense of how fast I was going is, you're going over the Pacific Ocean, and then 10 minutes later you fly over New York, and then 10 minutes after that you're flying over London.
If the ISS was orbiting closer to Earth, we'd all see how terrifying its speed is. It would cross the US from coast to coast in just 10 minutes, lapping the Earth more than 5,500 times a year.
It's actually traveling at 26,000 kilometers per hour, or 17,500 miles per hour, so definitely be breaking the speed limit, right?
Speed on Earth can be incredibly dangerous, but in space, at the velocity the ISS hurdles, the consequences of a collision can be off the scale catastrophic.
Space debris is going by you at about 5 miles a second, so if there's a big piece of debris that happens to have your number on it, it's moving so fast, you'd never see it.
March 23rd, 2012. Mission Control radios the crew.
And hello, relative velocity. Any idea? Checking.
Something is heading straight for the space station.
The time of closest approach of this fragment of space debris is 11 minutes from now.
No one knows how big this object is.
Well, you do what you're trained to do, and even though you got woken up in the wee hours of the morning, you know what the reason is.
The crew must prepare the space station for impact.
Can you see it? Yeah. Yeah.
You go through and you close every single hatch on station, which takes about 45 minutes.
Yeah. That's from which direction? Yeah, we don't know.
The hatches can withstand a sudden loss of pressure that would come from the hull being breached.
Coming up on the 6-minute mark.
If there is a puncture, any loss of air could lead to a serious emergency.
Coming up on the 3-minute mark until the time of closest approach.
The crew takes no chances. They head for the escape vehicles.
We floated into our Soyuz spacecraft with initial preparations for undocking if space station were to be hit.
1 minute from PPA.
And you just kind of hunker down and hope it doesn't hit you, and you just sit there and wait.
Looks like that's it.
Fortunately, this time it's a near miss. Risk to the integrity of the space station's hull.
Luckily, most of the stuff that's big enough to hurt us we can track. There are a few objects up there which are too small really to be tracked well, but they're big enough to do damage.
The ISS is constantly bombarded. Most of the debris is tiny, but even a half-inch fleck of paint could inflict the same damage as a motorcycle crashing at 60 miles an hour. To be a viable home, the ISS has to be able to take the hit without losing all its air.
The ISS basically has a bulletproof vest. So just like a bulletproof vest, which has different layers of Kevlar that can rip as a bullet enters it, the ISS has different layers in its outer skin.
The space station's skin is known as Whipple shield. The outer wall is made from a thin sheet of aluminum, less than 1/10 of an inch thick. Beyond that is a blanket of woven material, and a further thin wall of aluminum. It seems too delicate to protect the ISS from a direct hit.
It turns out that a solid piece of metal does not offer as much protective power as if you cut that metal into very thin sheets, spread them out a little bit.
When there's an impact with a high-speed micrometeoroid, it hits the to penetrate the hull.
It's kind of counterintuitive when you think about it. You know, that a whole bunch of sheets of aluminum foil could somehow give you more protection than putting them all together. But that's the way it is in space.
The Whipple shield has protected the space station from micrometeoroids for over 20 years. But it's ineffective against anything larger. If a large object on a potential collision course is identified, the only option is to move the whole ISS out of its way.
Space Command monitors most of the space debris that is out in orbit. They notify our mission control here at NASA. We look at that and we have a green zone, a yellow zone, a red zone.
Objects that fall within the red zone have a 1 in 10,000 chance of hitting the ISS. Too dangerous to ignore.
If we think that something is coming within the red zone, the space station can adjust its orbit and give itself a little boost to get out of the way.
Small thrusters change the ISS's trajectory, but using them is expensive.
Now these thrusters, you can think of them almost like tiny rockets, and those rockets are using propellant, and that propellant isn't infinite.
It all has to be sent up from Earth at a cost of $10,000 per pound of propellant. This brings engineers face to face with the greatest challenge of all: how to reduce the station's reliance on Earth. The ISS can't be self-sufficient if it relies on thrusters to move. But a clever trick hidden at its center means it doesn't have to. The International Space Station has a problem. It orbits the Earth every 90 minutes and has to be regularly reoriented. Using thrusters is one option, but that uses up precious propellant.
With the space station, if here's the Earth, we want to keep the station, usually, I mean, there are sometimes exceptions, but usually you want to keep the station in the same relative orientation towards the Earth so that the cupola is looking down at the Earth. And in order to do that, of course, the space station is going to be rotating once every orbit around the Earth.
What the ISS needs is a way to move that doesn't use propellant.
The solution for
But how can they move a beast the size of a football field, 1,600 RPM? The flywheels create a lot of angular momentum, and simply by changing the RPM, or tilting the plane they spin in, they transfer that momentum to the ISS, and the whole thing moves.
If I were sitting here in a chair and I had a gyroscope spinning around in this direction, and all of a sudden I put a brake on and slowed down the gyroscope, the chair would start to spin around. You know, I would slow the gyroscope around and then woo, I would do a big spin because that angular momentum has to be conserved.
So these 4 controlled moment gyroscopes can move the whole of the International Space Station, and there is not one single drop of propellant used in order to make that movement.
But they do use electricity, as does just about every piece of equipment on board. To supply the ISS's total power requirement, a whopping 75 to 90 kilowatts, engineers cleverly exploit the ferocious power of the sun. The station generates all its electricity for free.
The solar panels on the space station are absolutely essential because they provide all of the power that the station needs.
The panels have to be enormous, which would have made them impossible to transport had NASA engineers not come up with a genius way to get them into space.
What's really impressive about the solar panels, not least their size, around half an acre per array, but the fact that they are actually folded. And then once they're in space, they were able to be unfolded. Now that's an amazing thing to do in space.
Together, they can generate 120,
and then we can gimbal this direction.
One of the ISS's greatest engineering triumphs, it's been generating its own power for over 177,000 hours and counting. That enables round-the-clock air conditioning, fundamental to astronaut survival.
This cannot go down. It's not like a power cut in our homes where, we can get a torch or light a candle or something. If this goes down, astronauts will die.
When the ISS enters the shadow behind the Earth, the temperature can drop to below anything ever experienced on our planet. Without the protective cocoon of the space station, the ferocious cold would kill astronauts in a matter of moments. Conversely, when in sunlight, the temperature can soar.
Temperature and managing temperature on the ISS is very important. If you imagine the extreme temperatures that you can get on the ISS if you're facing the sun or not, could be plus 250 degrees or minus 250 degrees.
So you have these huge temperature extremes simply because of being sunlit or being in the shade. And it's something that you have to keep in mind when you're doing your engineering.
Of these threats, overheating is the hardest to manage.
With lots of people and electronics inside a spacecraft, you tend to generate more heat than you know what to do with. And so the problem in general, at least in Earth orbit, is that you've got to get rid of heat.
If heat built up uncontrollably inside the ISS, it would become a deadly incinerator. So cooling the station is a crucial priority.
Standard ways of cooling that we're used to on Earth don't work. Convection does not work. Conduction does not work.
Conventional aircon would be ineffective. Scientists had to come up with a cooling system for radiating heat away from the ISS. It needs to be liquid-based, but there's a dilemma.
Ideally, what you'd like to be able to do is just put it through a water cooling system.